All right. We'll repaste the link one more time here in the chat real quick. Welcome everybody to today's systems facing call. We've got a good topic for today. Just before we jump into the topic though, we had just a couple quick pieces of business to kind of for the systems facing track that we wanted to cover. Troy Bayer, who's been one of our track co-coordinators, has kind of indicated that he's going to step back from that role, still participate with us as a member of our community, but needs a little more time for other obligations. And so internally, we've kind of discussed that, and Betsy Hillary from Purdue, who's been part of our coordinator group, is going to step forward and take over that role. So Betsy's here on the call. She just was waving her hand a moment ago. So we both very much appreciate all the effort and time Troy has put into supporting the group, and we're excited to have Betsy in this new role. And we will be sending out to either the systems facing track and or people network wide just kind of a call for volunteers at some point in the short future for filling in our vacant spot on the steering committee side of things. So keep your eye open for that if you have interest. We very much would welcome anybody who's interested to come and help us out to keep things moving. So with that said, we have a great panel put together today, and Sai is going to kind of take lead on this one. So I'm going to turn things over to him to introduce the topic itself and our panel members, and we'll go from there.
Hi, I am Sai Pinepalli with Louisiana State University Center for Computation and Technology. The topic for today is data centers and cooling in particular. We wanted to introduce the aspect of cooling for various systems facing professionals. So we have 5 panelists. So let me introduce the first panelist. He is Rich Donaldson. He is with KW Mission Critical Engineering. He has over 20 years of experience in strategic planning and design of mission critical facilities and HPC environments. His experience in total cost of ownership evaluations and optimizing cooling solutions and alignment with customer requirements. For this particular presentation, we asked him to use his experience with the recent Georgia Tech data center installation. So we hope to gain from his expertise. Over to you, Rich.
Very good. Good afternoon. I do have a couple of slides here just kind of share. Just want to go over some kind of call it liquid cooling 101 for how it applies to HPC. So let me know if you're seeing that.
Yep, you see that?
Yep, very good. So the little lag on the system here. The basically for liquid cooling, it basically breaks down into 4 different classes. And ASHRAE recently, with the publication of their TC 9.9 guidelines, kind of changed these classes up a little bit. You may have known them previously as W1, W2, W3, W4. Well, now they've changed it to a W17 for if you're supplying water up to 62 degrees to your high performance compute load, W27 if you're up to 80 degrees, a W32 for 89 degrees, and a W40 for 40 degrees. These are the Celsius, and these are obviously the Fahrenheit conversions. ASHRAE is still doing their best to get us engineers used to this metric system, which is still an ongoing effort. How does the HPC operating class requirements impact you as a user? Well, which class you choose to deploy is going to impact the first cost of your cooling system. It's going to impact the operating cost of that cooling system, as well as potential reliability. So as we'll show through here, here's what a system might look like for a W17 or W27. So a lot of parts and pieces here. You'll see here's your high performance compute load here. But to keep that cool, typically we might need a cooling tower sitting outside rejecting the heat. We would have probably some sort of a heat exchanger that allows us to decouple the precision water we need at the load from this open cooling tower loop. Because this cooling tower can't provide us the temperature we need when it gets really warm outside, we would probably need some sort of a chiller to do some additional cooling on that. And then we need pumps to move that water in these two loops. If we kind of look at the amount of power we need to cool this load, if we start here at the cooling tower, 20 kilowatts per 1 megawatt of HPC is a good benchmark. When that chiller is running, it could add up to 80 kW of power consumption. And these two pumps are going to be at 15 apiece. So right there, you see we're at 130 kW of power to cool 1 megawatt worth of compute load, in addition to all the initial cost of all these parts and pieces. So as you see here, the W17 and the 27, while they are very, I'll say, reasonable and somewhat classical in their temperatures, you need a lot of parts and pieces to make it work. If we now look at the W32 system, now we're looking at 89-degree water. You'll see here that we've simplified it a good bit. We still have some sort of a heat rejection cooling tower outside, still at 20 kW per 1 megawatt. We still have a heat exchanger, but now with this higher temperature, this cooling tower can now make the right temperature, and we don't need the chillers. And we still have a couple of pumps, but now you see we've reduced that cooling down to 50 kW per 1,000 kW or 1 megawatt of HPC load. And finally, if we go to the W40, which says, hey, up to 104 degrees to your server, now we've essentially can make it even simpler, where we just have what we'd call a dry cooler. Think of it as a car radiator sitting out here. It's a closed loop system and just one pump. Now we're down to 35 kW of power to cool 1 megawatt of compute load. And we've done it with just a couple of pieces of equipment, some simple piping. So you see here, it's lower first cost as well as lower operating cost to cool the same amount of compute load. And finally, just as a quick little recap of the Georgia Tech HPC, it's this facility here. It is adjacent to a high-rise tower that's part of the campus. So the first floor had our tier 1 compute system. We had some enterprise as well as some co-location in here. So again, this one building was housing multiple data center functions within the same plant. And we did try to incorporate some waste heat recovery, rainwater harvesting, and some other rather cutting edge components to make this a very energy efficient and useful system for Georgia Tech. And that's the end of my presentation.
Hey, thanks, Rich. Just a reminder, all the participants are requested to post their questions either in the chat or preferably in the call doc. The panel is going to be driven by your questions, so please ask your questions or make your comments over there. The next panelist is Doug Johnson. Doug is with Ohio Supercomputing Center. He is the associate director over there. He has worked as the chief systems architect and HPC manager. He is active in the CARC groups, and he has actively worked presenting various topics to different groups, including as early as Supercomputing 2001. Doug?
Thanks, Sai. Let me share my screen here. I've got a couple introductory slides to go through. Let's see. Does that look okay for everyone? Good. All right, so I'll be brief. Go into why OSC deployed warm water cooling, the design of the Pitzer cluster and its warm water cooling system, as well as a brief discussion of the results and our impressions of it. So, I think Rich gave a great introduction that showed some of the benefits and some of the points that he didn't touch on. Maybe it's just really hard to cool some of the modern systems with the amount of heat dissipated from the processors and the GPUs with air. So everybody is being pushed to consider direct to the chip cooling in one fashion or another, or at the very least, cooling at the rack level. There's some other benefits that are kind of second order. So if you have direct to the chip cooling, you can have lower fan speeds in the servers. And I'll go over some of the numbers that we've seen as a result of that. And if you're cooling with water directly to the chip, you can also have a higher set point in your server room. The equipment that we have today is rated for much higher temperatures than the 18 degrees Celsius that seemed to be a pretty standard set point for server rooms in the past. There's no longer that much of a need to keep it like a meat locker. And there were a couple of things that pushed us towards this. We're in a data center that was not purpose-built for high density or HPC. And we don't have any chilled water available in our space, and the chiller plant in the building is just not large enough for the scale of systems that we put in. We've got a good condenser water loop, and for Rich's slides, he's let me know that we've got updated terminology. So we kind of have W32 water. So anything below 89 degrees Fahrenheit, it's not really a W3 loop. It's probably a W4, but there's a couple things. It doesn't get much above 89 degrees Fahrenheit wet bulb in Columbus that often. So we get some good evaporative cooling in the warmer days. And we're on the 4th floor and a long way from the towers. And so we actually get some cooling because of the runs for the condenser water loop. So we don't see anything above 89 degrees Fahrenheit. So I say that we have a W3 water loop. OSC pays for our rent and power out of our operating budget. And so we're motivated to be efficient. Not that we wouldn't be motivated to be efficient and good stewards of the taxpayers' money anyways, but this definitely makes it all that more critical. And we do have to pay for any kind of improvements to the data center out of our own funds. And so that also motivates us to try and put as much funds into the systems rather than the facilities. So it's a balance that we have to walk. So we've had the Pitzer cluster since 2018, and we've since upgraded it. And I know that this is a little bit of an eye chart, but the bottom line is it's 658 nodes. It's a pretty medium-sized system, and we've got direct to the chip cooling for nearly all of the processors in the cluster. I'll come back a little bit later about what's not water cooled, and we can touch on that a little bit. So to kind of go a little bit nittier grittier into the diagrams to expand on Rich's diagrams, we get that condenser water loop run into a CDU, a coolant distribution unit. So we've got a secondary loop that has the heat exchanger with that condenser water loop. And then that is in turn circulated into rack manifolds and into the individual servers. And you can see what a dense rack looks like. There is a little bit more to work around, and you have to be a little bit more careful so that you still have a manageable server install. Even though OEMs have these as supported products, it's very easy for the final integration that they build and design to result in cable or hose runs that make it impossible to work on. So it does have some upfront costs for paying more attention to what the physical layout looks like in the rack and making sure that everything works right. And then ultimately you get into the server and the specially designed cold plates for the processors that they support. Replacing the heat sink, as well as most important, or let me restate, also importantly, removes the need for some of the airflow in the system. So what are our results? After the upgrade, when we brought in the Pitzer expansion and a slightly more efficient CDU, a newer version of the coolant distribution unit, we've seen an increase in the percentage of the heat rejection to the warm water loop for the cluster. So approximately 64% of the heat dissipated from the cluster goes into the warm water loop. GPUs, power supplies, any network switches, and some of the more exotic nodes are all air-cooled. And with that warm water loop, we see a very consistent temperature for all of the processors. So this may have implications for application performance because turbo states or higher frequencies may be accessible for longer periods of time or more consistently. One of the second order effects that I mentioned is the lower chassis fan speeds. And we estimate that that actually saves about 5% of the power for the system. So fans can consume a non-trivial amount of power for a fully loaded system. And we've also been able to reduce our data center space because of denser installs. We would like to see more options from vendors, especially better support for GPU cooling. That's it.
Thanks, Doug. I want to introduce our third panelist. That's Jonathon Anderson. Jonathon is with the University of Colorado at Boulder. He's the Associate Director for Research Computing. Some of his responsibilities include research computing systems operations. He's also the Director of cybersecurity infrastructure. His experience includes systems, cluster administration, design, and automation. In the past, he has worked with Argonne National Labs, King Abdullah University of Science and Technology, and Icahn School of Medicine.
Thanks, Sai. That's true, except for I'm not a director of cybersecurity of anything, so I'm not certain where that came from, but the rest of that is accurate. Our primary HPC facility is what we call the HPCF, or the High Performance Computing Facility. It's in a parking lot, so we tend to not put as many pictures of it out, but I expect that this is a fine audience. It's not as far along in the cooling realm as the presentations we've had before. You'll recognize the parts of what I'm going to show as what Rich referred to as lots of parts and pieces. So that we have improvement to in our future, I think, but we've been struggling to move towards a full water cooling situation. So, you know, you'll recognize, let me see if I can annotate here. Yeah, here we go. You'll recognize the parts. This is our heat exchanger between the internal loop and the external open loop. We have our two pumps, exactly like on that diagram before. We do have a chiller over here, although the Colorado climate, thankfully, means that we're able to run just on free cooling for at least 9 months out of a year, sometimes up to 10. So we get pretty good efficiency out of this system. And then with that, we're, now I can't, how do I stop annotating? Okay. And then we're doing a pretty normal data center system in here. Let's clear these, clear all drawings. So, you know, our floor plan is what you would expect. We have an interleaving of data center racks with these crack or craw units. And so we're cooling the air within a confined hot aisle, but nothing direct to the nodes, though we do have pretty good density in how much air we're able to cool. So we're able to put a pretty high thermal load into this environment in our two hot aisle containment pods. But we're running up against the same restrictions that that Doug referred to. Maximum a maximum TDP on CPUs for non-direct water cooling. And every time we deploy a new system of a given size, we start trying to have a conversation between usually Dell, but other vendors as well, and our data center team, which is an external entity to our research computing group, about what it would take to bring water direct to the chips. And we've just struggled to get the right people in the room to commit to, yes, what you have on site is sufficient and will work. So every time it comes down to a matter of deadline, and we just end up building within our existing thermal capacity and ability to cool it. So I don't have much to say beyond what is traditional and what we're doing in this environment. We want to be doing direct to chip water cooling, and we are definitely hitting limitations in what we're able to deploy in this environment as a result of our air only cooling environment. But we've struggled to get cool IT into the room, I guess is where it comes down to it.
All right. Thanks, Jonathan. Our next presenter is Chris DePrater. Chris is with Lawrence Livermore National Labs. He's a systems engineer there. He has over a decade of experience with HPC systems. His responsibilities and skill sets include building controls and mechanical systems. He's a member of energy efficient HPC working group. He has worked on multiple top 500 HPC systems. He's currently working towards exascale at Lawrence Livermore. Chris.
Thanks. Let's see, how do I share my screen? Can you hear me?
Yep.
Due to time factors, I kind of hijacked my boss's PowerPoint, so which she was okay with. So I'm going to kind of skim over the things that aren't really too relevant to cooling. But anyway, my name is Chris DePrater, and I've worked at Lawrence Livermore since 2002. And I am a systems engineer, which I'm responsible for the building controls and cooling systems. Our site is about 1 square mile. It's a DOE facility, but we are managed by several groups. And there's some info on the slide. It's our mission is basically to enhance the nation's defense from global threats through science and technology. A couple of our platforms. Let's see. Let me skip this one. So here's some of our previous platforms that we've had in the past. We had the early systems with C7600, the Cray ones, which were actually immersion systems in the late 80s. From Purple is where I came in, is my actual first machine I got to work on. Blue Jean, Sequoia, Sierra is our current system, which we're trying to go to exascale with El Capitan. And I'll show you some slides on how we're preparing for that. So kind of our way about planning for these systems. We have to consider performance parameters such as the cooling capacity, the power capacity, seismic, and structural. we identify those gaps. We develop, well, I started in the middle, but we first develop the facility requirements, then we demolish what we need to want to get to the cooling slides on here. Here's a power slide. So part of our mission to get to exascale is we need to bring up our facility to 85 megawatts, and we need to increase our cooling capacity to 28,000 tons, and we need to have a site that can hold up to 625 pounds per square foot, and also upgrade our building management system. Here's an overview of our site. Here's our main building, which will be at, it's at 40 megawatts now. Once this construction is complete, which is right here, we're building a new switch yard. We installed those new cooling towers, and then we're piping in 30-inch pipe from heat exchangers into our building with 30,000 GPM, which it would be W3 water up to 89 degrees Fahrenheit. Here's a little close-up of the new construction of our cooling towers. There's our 30-inch pipes going up above our chiller room, and up over, we have 3 taps that will actually penetrate the building and have a capacity at 10,000 GPM per tap. We're bringing in a 115 kV line to the substation, which then would transform to 13.8 inside the building, and then to 2.5 megawatt transformers, and then again step down to 480 to feed our computers. Here's our electrical distribution, our mechanical distribution, which we will still have about 10,000 tons of chilled water and 18,000 tons of the new W3 water. We site several systems in our building, so we have a need for different temperatures. And another facility, we have just straight adiabatic cooling, and that which is a little bit more complicated because you are relying on the wet bulb temperature. So on those high humid days, it could be a challenge. But our air handlers in that building serve 2 purposes. They have liquid cooling capabilities as well as air cooling. And that's our facility. It's building 654. It was built modularly, so it can expand out to the north when we can knock out that wall and then expand our facility as we grow. I did not mention that our systems at Lawrence Livermore have a life about 5 to 7 years, so we're constantly in construction. We always have a need for more space, newer technology, and we're always in contact with the vendors with the latest and greatest technologies that they have, so we can stay ahead of the curve and keep citing the new systems. That's about it for me. Thank you.
Thanks, Chris. Let me introduce my next panelist, Nathaniel Mendoza. Nathaniel Mendoza is with TACC. He's their senior network engineer and CISO. His projects included TACC resource security, building the TACC complex. He, as CISO, holds a CISSP. His HPC involvement includes work with SINET as physical security chair and network security chair. In the past, he has worked with NICS at the University of Tennessee and San Diego Supercomputing Center, Netcom Systems, and LA Valley College.
Hey, everybody. How's it going? It's good to see some familiar faces. So you missed the lead there. So Troy Bear and I built Kraken 10 years ago. So, some familiar faces here. I know a couple of you guys. So it's pretty good to see everybody. So I don't actually have any slides to make this simple. What I do have, though, is I have a virtual tour that I put in the chat. So you can take that at your own leisure and kind of work through it. We are TACC. We are the largest academic computing facility now. We just recently won something called the Leadership Class Computing Facility, which is large infrastructure project for NSF. So we have a kind of everything. We have Stampede 2, we have Frontera, those large machines. So Stampede 2 is air cooled, Frontera is cool-IT cooled with on-chip radiators. We also have some high voltage DC. We got a ASHRAE. I got some Green Revolution in here. So we kind of have it all, and we're kind of a mix. And so we kind of have a lot of breadth of experience kind of working with everything. We will be bringing on a 20 megawatt facility in the next couple of years to add some more capacity. The thing that we find the most is we kind of do it the inverse is we build the cooling to the machine, right? So we're kind of opposite of kind of how we go. So we just kind of build what we need to make sure the machines will work. And, our number one thing when we do our grants and our proposals is to make sure that we can get the most bang for our buck for computing wise. And then we figure out how to do the rest. It is Texas, so I run chilled water here. I got about 12 megawatts of cooling on the chillers. We're gonna be adding to that soon. I also do probably another 3 to 4 in air and dipped. So for us, it's GRC. So overall, our footprint's probably to 15 to 16 megawatts when we're running hot. And, we just kind of have to be a master of all trades kind of thing because, we deal with kind of everything, right? I spent more time under the floor with cool-IT and CoolTerra. I know more about cooling than refrigeration I ever want to know. I know, I do know, neat trick that we finally learned is, the coolant from cool-IT will phosphorate under black light. So that's a good thing we didn't know for a while. We've seen, I'll show you the horror stories. We actually had a leak of the cool-IT system at one point, and we dropped about 80 liters of the coolant under the floor. It looked like a horror film. So, we've had a lot of fun playing with these things. So, any questions you guys want to ask us about these things, we just kind of have to do a lot of weird things. And because we're an NSF center, we don't have these persistent funds. So we get grants and we upgrade the things and we go forward, right? So our number one issue we have right now is power. We're trying to standardize on a power system. Is it 413 or 415? We think it is. But, my problem is I have one half of my data center that's Delta, one half is Y. Leads to some weirdness, right? So, we just kind of deal with these things as we go. I see we're shaking our heads, but, it is what it is. I don't have budget to buy another $250,000 transformer, right? So, these are kind of the uniquisms of working in HPC and academia. And, it is Texas, so it's hot. We need a lot of cooling, and it gets really hot. Or it gets really cold, it turns out, like it did a couple weeks ago. So it's been quite the dichotomy of the year. I was asked briefly to speak about what happened during the ice storm here. So we haven't had this kind of thing before. It's kind of unprecedented. I will tell you, we didn't do anything. We shut everything down. And what we became a refugee center for our staff. So during COVID, it's particularly tough, but most of our staff lost water or power or some combination of those two. And we literally became a refugee center for our facility. So we tried to social distance people. People slept in offices. We had food going, we had coffee going, but really, it became not a power issue or a cooling issue, but really a humanitarian issue. And how do we care for our staff and make sure that they are doing the best they can under those trying circumstances. The only big issue we had was coming back up was there were about 7 broken mains around our campus here. And there was enough water in the system, but they were afraid they couldn't refill it if we were a little low. So that was the only real gotcha we had coming back. And so I'm here to answer any questions and enjoy the tour.
Hey, thanks, Nathaniel. Rich, let me circle back to you and ask a question based on what Nathaniel mentioned. You are in Atlanta and you design systems for a lot of places. How do you design systems, especially cooling, based on different geographical locations?
And that is one of the key things we look at. A, what is the temperature we're trying to achieve with that loop? And then B, what's the worst case ambient we want to contend with outside? And that's what's really going to drive your selection. Can you get away with a dry cooler type range where you don't have to have sprayed water and consuming water to produce that cooling effect? Or is it going to be hot enough or wet enough that you're going to have to use a cooling tower, which again adds a little more complexity to your system, a little more cost, but it allows you to maintain those desired temperatures if you are indeed looking for that class W32, you know, if you keep it around 80 degrees or so, then the cooling tower will work with those parameters, where a dry cooler might struggle if it got above, you know, maybe 100 Fahrenheit. So that's really what the engineering does, is we have to look at the two constraints and figure out the best fit to meet that requirement.
Doug, Jonathan mentioned that Colorado's temps help him to maintain certain things for 9 to 10 months of a year. How does your environment help you with your infrastructure?
Well, we've been really fortunate in that there have been some quite warm days where we are above 89 degrees Fahrenheit wet bulb, but we haven't seen that reflected in our condenser water loop. And I think that, you know, there's some environmental factors inside of the building that are, you know, we're basically getting some pre-cooling perhaps, even though the pipes are insulated. I'm not sure that I fully understand it. And the building engineers have never really explained why it's so cool. It's not like they're using city water to keep the temperature down or anything like that. It is they try to keep it as closed a loop as possible, just replacement for evaporation. So we were expecting warmer temperatures, but we haven't encountered them. But it's we've got a little bit of headroom within the system. So if we do have a warmer primary supply, the chips, you know, we run at about 40 Celsius for the processors. So there's a little bit of headroom there. They're much cooler than the air cooled.
Oh, thanks, Doug. Jonathan, have you experienced any adverse weather conditions that impacted your expectations?
The only time weather really becomes a factor for us, our cooling system is non-redundant, even between the chiller and the tower, because it's using the tower as the heat sink for the chiller. So we have to take the system down for cleaning of the external tower. And that limit, when we have particular, especially in the winter, if it's too cold or too icy, we have trouble maintaining it. But in terms of its ability to cool the system, not really. It just, you know, the BMS system brings the chiller on and off when it's required, but otherwise we see good efficiency out of it. And I think it's mostly about the humidity than the temperature that we have here, because it's relatively dry.
Chris, how does your geography affect your architecture and the technology of your choice?
We're in a cooler, dry area, so for the adiabatic cooling, it's really beneficial. We do run into some issues every once in a while in the fall and the spring, but mostly we have really good water quality as well. So we get a lot of cycles in our cooling towers. So I could probably run 75-degree water all year long on our cooling tower.
Nathaniel, does being in Texas impact your choice of technologies, and what technologies do you normally prefer?
Well, so it has impacted several things. One, it is hot, very hot. I moved here 10 years ago, and I immediately came into 100 days of 100 or 110 degrees or better. And that was a lot. We do actually have a thermal storage tank. So 20 hours a day, we run off the chillers, and then at night we pump the tank. We pump the tank full. We run off that. It does lead to some interesting temperature fluctuations. We can definitely tell when we're coming with the tanks. We still get some spikes and heats. But you know, we really have to, it really is like living on the sun out here sometimes. So really have to prepare for these things. And so, our upscaling of our chill water supply, we're looking at doing warm water cooling going forward, but, we still, we're currently running 6C in the data center, which is cold, but we kind of need it right now with the mix of the air and everything else. But, we really have to make our cooling systems beefy, just because not just count for that T load, but also it's just hot, right? Anybody opens the door, all of a sudden you get a bump in temperature, and people coming out the door all the time. So that's really what drives this, is really Texas heat.
Rich, you already answered a question or two about ASHRAE standards, and if the temperature is over 40 degrees Celsius. Do you want to add a little bit more to whatever didn't fit in the chat?
No, I think the one that did stick out at me was something that is probably going to be encountered by, one or more of this audience at some point, which is you've got, or you're going to inherit an existing facility that maybe it's just air cooled, maybe just has some DX type equipment. There's no real chilled water loop available, but you're bringing in some HPC that's going to need some water to the rack, water to the chip. So what do you do? And the good news is that there's solutions out there. The cooling distribution unit, the CDU that was mentioned earlier, is a very flexible piece of equipment. It has the ability, obviously, to push that water to your rack, to load, but then where it rejects that heat, maybe it can be done as an air-cooled system. Maybe it can be done to a chilled water loop that you're dedicated. You put in a dedicated chiller, or if you maybe if you can live with warm enough water, maybe it's going to a cooling tower or a dry cooler. So, and the nice thing about that CDU is it also can be programmed to where that loop temperature that it's moving out to the chip should also stay above the dew point of the room, so you don't have to worry about sweating of the piping or sweating within your rack. So there's some nice features that CDU brings to the table. Again, it's that pump and heat exchanger you kind of saw pictured in those schematics, but it's in a nice simple box that doesn't take up a lot of space for, say, in the neighborhood of 100 to 200 kW worth of heat transfer.
Doug, you mentioned going from 18 degrees Celsius meat locker type of data center to the current standards. How did you make the transition, and what kind of resistance did you face from data center or systems professionals about those kind of changes?
So sadly, we haven't increased our set point yet. So we're still running the room fairly cool. We are waiting to have better instrumentation at the PDU level. We actually don't have continuous power collection, numbers from our PDUs, nor from the cracks. They're recorded, but we just don't have that networked right now. The facility just was not built for that. So we don't want to start increasing the set point in the room until we can better quantify the effect of power consumption as we do that. I think the biggest barriers to it is making sure that all of your equipment is modern enough that the higher ambient temperatures are supported for that hardware. So legacy equipment may be problematic. And I know a lot of people are still running systems longer than most people would like. I know we've had to do it. So that's probably the biggest barrier, is that you need to be sure that your equipment can handle higher temperatures in the room.
Jonathan, how do you work with these new ASHRAE standards?
The honest truth is it's really outside of my expertise. We defer most of that to the campus data center team, and they handle making sure that our data center is in spec for the equipment that we're deploying. But I'm not personally too up on it.
Chris, do you want to comment on that?
Sure. I actually kind of have an interesting story on that. We have similar thoughts, like Doug was saying. But so what we did was we actually raised our chilled water set point 1 degree per month for several months until, and our room set point until we got to the desired set points. We made sure it was okay, and we looked at all the equipment and made sure that we wouldn't have any adverse effects. But getting that mindset out of a lot of people's heads was next to impossible. So we kind of just did it, and just did it in very slow increments. And then when we got to where we wanted, we advertised it, and now I think our chilled water system went from, I don't know, I think it was 42 degrees to like 49 degrees. And also our data center went from like 60 something, 67 degrees to about 72 degrees. So that's how we handled raising those temperatures in our data center.
Nathaniel, do you, since you are in Texas, do you tend to be on the higher temperature side, or do you follow the old standards?
So, you know, we'd like to raise the set point a little bit just because cost savings, right? We've done the math. We will save substantial money. The problem is we have several generations of gear, and not everything can handle it. So I still have a ton of air-cooled stuff on Stampede 2. I have a ton of IT gear. Just, you know, I have Chameleon over here. I got a bunch of stuff, right, that just is old school. And, you know, we have some very old cracks that are running still. So we want to raise it just to save cost. But, you know, because we have such a just such a weird mix of hardware, it's hard. We're going to redo these things soon, but you know, we all want to see the cost savings, right? Because, you know, we joke that, you know, a megawatt is cheap for us, but it's really not, right? You know, that if we can save, you know, a megawatt a day just by being better about our set points, you know, that's millions of dollars we can then use for other things. It's probably more appropriate, right? So from a cost savings perspective, we'd like to. With the new Cool IT, you know, because you know, I see some of the chat about Motivair, all those things. I don't see a day where we're not going to be building some sort of on-chip / node plus cool door for the future, right? I just think that's the way it's going to go for a while. And those things take a lot of specialized things. So, you know, once we get those things more ubiquitous in our environment, then I could probably do better about raising it higher because they're a little more insulated. You know, our biggest problem is we have the liquid cooled Mellanox switches, and those things are really hot. Even when they're not, even when they need some air. So yeah, that's our answer. We'd like to.
Rich, let me follow that up with a question in the doc, which wants to talk about the effectiveness of rear cooling doors versus direct to chip. And like, is there a preference, a combination, or how do you transition to those?
It's really going to be driven by the manufacturers. Right now, we kind of see the rear door cooling as, I'll say, a supplement. If you've got a data floor where all of a sudden you have to deploy maybe 3 or 4 very high density but still air cooled IT racks, then that rear door solution is a good way to handle that. You know, maybe it's as high as 30 or 40 kW per that rack, and it would just overwhelm your conventional air cooled system. Putting those rear door coolers on there can really help capture that heat before it goes back into the space. So I kind of use those as a neat little tool when I've just got a limited number of air cooled racks that are going to go in, and I'm just not comfortable that the conventional air cooled perimeter crays or cracks are going to be able to keep up with it. So that's where I see it. I don't see that as a long-term, that's where you're going to go. I think the long-term solution is water to the chip, water to the rack, because now you reduce or eliminate that amount of fan power that those servers are going to be using. And that is becoming a major chunk of energy that kind of just gets forgotten about. But we're doing everything we can on the infrastructure side to get you very efficient chillers, very efficient cooling towers, to reduce that operating cost. And those fans are still consuming a lot of power that doesn't really get cataloged in any conventional system.
Doug, about getting cooling to the chip, you and Nathaniel both had some mention of Cool IT. Who are like, is that decision dependent on the kind of manufacturers that you work with, or do you have a lot of options? Who are the players in that industry?
Yeah, so we work with the OEMs, and so each OEM has their preferred vendor for the cooling system. And I'm not too up on who the other OEMs are using, but I think all of the major OEMs have direct-to-the-chip as an option, and whether it's CoolIT or Motivair or some other company, uh, you're really constricted by who your OEM works with and which systems they will support and what platforms they include water cooling as an option for. It's still early days. There's much better choices than what we saw just a couple of years ago, but you're still going to be limited to certain platforms, and combinations of hardware may not be supported.
Yeah, so we when we initially built Frontera, we were working with the internal Dell team for their cooling thing, which they then discontinued. I'm sure all of us kind of ran into those things, and we luckily CoolIT has an OEM called Coolterra. We know them quite well because they came out and helped us. So it turns out Coolterra manufactured the CDUs for us through CoolIT and the doors. And so when we built Frontera, the problem we're having right now is all we have is chip cooling and nothing else, right? So we're still generating a lot of load of heat of everything besides the chip. So memory, GPUs, all that stuff, right? So that's what we had to supplement with the cool doors. And also ours are 58U, so they're ginormous, right? The joke I used to make was, oh, we're pushing around Toyota every time we push your rack around. I looked it up. We're pushing around a BMW 3 Series. Toyota doesn't weigh as much. So, that's kind of the so when it's all said and done, when we have the 3,100 pound shipping weight, when it's all said and done with the door on, it's roughly 4,000 pounds of machine, right? So, those scales are silly, and finding the right people to do it. So, Motivair, CoolIT are the number 1 and number 2 players. People are getting a lot better about these things. As we get better cooling for GPUs, it'll be great, because those just eat so much energy for cooling. And then, we still have, our as Doug put them, our non-standard systems go into either air, but for us, they go into the oil, usually how we put them. So we have 100 GPUs running in a CoolIT tank, a GRC tank now, and that thing is just pulling very little data, and I literally have 1 half-inch pipe going to it. So there you go.
Rich, let me circle through the panel and ask what kind of advice, since we are coming up to the top of the hour, what kind of advice do you have for people about how to implement their cooling? Anything to summarize this?
I think the takeaway I would have is, as you start looking at, what type of racks or IT you're going to be using, and you are settling in on a liquid to the rack system, the more you can live with an elevated temperature, or the more the manufacturer can say they can live with that elevated temperature, the simpler to support that cooling from both a CapEx and an OpEx standpoint is going to be. So the higher is better. And again, with what the manufacturers can support. So that's really the takeaway there is, like was mentioned earlier, we're not making meat lockers anymore. These are, an 80-degree room is not going to be unheard of from a data center standpoint.
Doug, your advice?
I would recommend having discussions early in the procurement process, either in your RFI or RFP. Have your facilities people in the room with the OEMs. Make sure that there's good communication there. We don't have a dedicated facilities person on the OSC team. We kind of do it on the cheap. And so, I think we've demonstrated that it can be done. We've got a successful project, and it was not an overly burdensome addition to the amount of work that was required for the cluster.
Jonathan?
My advice will be similar to Doug's. I think the more legacy you have that you're trying to retrofit water into, the harder it will be, and the harder it will be to cross that threshold. So if you're deploying new space, try and get water into it, at least as a proof of concept as soon as possible, just so you can get your facilities people on board with the process and have proven that it is possible. Because I don't expect it would be impossible in our environment. I don't expect it would be an incredibly onerous lift, but just getting everyone on board that it's worth the effort is the hard part for us. And crossing that threshold early is better.
Chris?
My advice would be in any of your new designs, and whether it's a new data center or just an extension of anything, is to design in as much flexibility as possible. Don't cap things, valve things. Develop it really an OPR before the design process even starts. Owner project requirements, and get all the players in the room. Make sure the future is thought about, but because technology it advances so fast, painting yourself in a corner is a common thing. So just a lot of flexibility as much as possible.
Nathaniel?
Yeah, I mean, so we're very lucky here. Dell is down the street, and we didn't go out setting to choose Dell, but it was really convenient, and spending time with those guys and really get to know these guys, and we are just incredibly lucky that I can call people and be like, hey, this is weird, come on over. So not everybody can do that, because as we're building the racks, we actually got to go inspect the racks to make sure they're built to our standard and there's no weird routing, which is very nice. That's just a quick 20-minute journey up the freeway, but really making sure that your vendor sets are you're getting the right team around, right? I'm not going to speak ill, but but I will. We work with IBM here. I got 27 marketing guys in every call, and that doesn't help anybody, right? So making sure you get the right team of people, and people you can trust is number one. And but also recognizing that, hey, sometimes these people are not appropriate for this thing, and you need to go. So just being strong in your voice and making sure that the right people to contact, because that's the number one thing. The IBM method of 27 marketing guys. It's not fun, and nothing ever gets done. So that's my number one advice is good vendor relations. We are human, and people want to be treated nicely and with respect. So that's how I try to keep things moving forward.
Thanks, Nathaniel. Thanks to all the panelists. We know that we barely scratched the questions that were posted in the doc. So we will send them over to the panelists, and if they choose to answer some of the questions, we'll send it out to the list. Back to you, Brian.
All right. Thanks, everybody. Thanks, the panelists, this was an excellent conversation. Thank everybody for attending. But with that, we will go ahead and close out today's meeting and look forward to the next one.
Thanks, everyone.